what I plan to sort of discuss is that there are two things essentially in gravitational collapse. Um, One is, of course, the numerical scheme which is involved. Um, it's a problem where you have Einstein's equations, and then you have matter field which is undergoing gravitational collapse. So that posits itself together as a problem which is not analytically tractable, except for few cases like there's Oppenheimer-Snyder collapse. You can find out what is happening, but then the problem has been, I mean, not it hasn't been tractable for a long time. Subsequently, in 1993, there was a breakthrough when Chopwick did a numerical run and especially found a certain uh, way gravitational collapse happens. And in particular, there is a scaling relation which is involved. What he essentially did was that he basically found, this is Chopwick 1993, and after that there has been a plethora of work in numerical relativity. This is something which is referred to as the revolution in NR. So what he basically looked at is he found a family of solutions. Okay, uh, let's call it S of P, where P's are the parameters. There could be different parameters which would be there, and with these solutions, he found that there's a property that for a value of parameter, let's say P star, you have there is a separation less than P star and greater than P star when you would form a black hole, and in the case the black hole will not form. Okay, so there is a particular parameter P star. Less than that, you would not form a black hole. Greater than that, you would form a black hole. And so this was and this the solution which he found were universal in the sense they were valid for almost all initial conditions. Okay. So it's a universal scaling, and in particular, he found that it's independent of the initial conditions, and in particular, he found that in the limit P equal to P star, there was a, it basically gave you critical phenomena. That is, you started seeing structures appearing at smaller and smaller spatio-temporal scales. That is both in the temporal region as well as in the spatial sector. So, and in particular, in this limit, the black holes which formed, the mass of the black holes, they were proportional to P minus P star to the power gamma. So they had this scaling relation. All the masses which were formed, they obeyed this scaling relation for all initial conditions. And in particular, this gamma exponent was found to be 0.37. Pardon? Yeah, so P could be different. So P's are basically, they represent, as I said, parameters of the matter sector. So for example, if it is a scalar field which is undergoing collapse, the profile of a scalar field will decide for you these parameters. And of course, the total mass, which is given by the ADM mass or something which should be there. Okay. So these are basically parameters in the problem, parameters of the matter sector, and there can be different parameters. For each parameter, you take any parameter you want. Each one of them will have a particular P star for which there would be, which will basically demarcate a zone for which there would be a black hole which will form and the other zone where the black hole will not form. And in particular, as I said, there's this universal scaling relation which arose, that masses of the black hole which formed, they obeyed this particular relation where gamma was 0.37. Okay. Pardon? It does not matter. Yeah, yeah, it does not matter what P is. Okay, so there are different parameters for each one of them. This is, it does not matter what P you change. You can, so suppose I have 10 parameters, I can keep 9 of them fixed, take one of them and change that one parameter. So that for that parameter there would be a one value, and again, so it will separate less than or greater than that. Okay, so this is what you have. This is what was discovered, and as I said, after this, plethora of work came up in numerical relativity, especially in gravitational collapse. People tried to looked at modifications of this, and various things have now sort of gotten developed. Now, for anyone who is sort of getting into NR and especially gravitational collapse, there are again a lot of problems which are still unclear and in the open domain. So, question is where to start. Often, sometimes people come up with that. So, Choptic's code was written back then, but nowadays the computing power has improved a great deal, and in fact, there are various codes now available which can run on either on your laptops as well, and in very short time. So, the one thing which I am going to sort of discuss in the course of today's lecture and tomorrow is this particular code by Leonardo Wernick, 2020. They actually wrote two codes. One of them is called SF collapse 1D. Okay. These collapse models are often studied in one dimension. This is what originally Choptic did. That is, you suppress the other dimensions and you do work in the reduced 1+1 configuration. So this is that one. This is written in C, but it has some Python wrappers to work around. And then it uses the standard formalism, which is the ADM formalism, which is what Choptic used. Subsequently, there are other formalism which have been developed. So there is a BSSN formalism which is there. The thing with the ADM formalism is that the way equations are written and everything, they cannot be generalized to any other problem. With BSSN, it is possible to generalize those to other problems. But for the lecture, I will stick with the ADM, because that is the simplest one to sort of understand. Once you have the knack of it, the other thing is easily possible. So there is another code is something like NPy critical, which is written in Python, is based on NRPy plus routines. Okay. So this is that, and then recently there was another code which came up in Julia. So it's something called spherical collapse.jl or something. So these are upcoming sort of, Julia is the next one which is there. So Julia code is also present. You can find by Berkzy et al. Okay. The advantage Julia offers is where Python is a language which was not meant to work in parallel. So you basically already only have serial codes. Julia allows you to work in parallel with the simplicity of Python and the speed of C. So that's the idea there. So for us, it will basically, what I'm going to be talking about is this one, the simplest one. So the idea is to basically give you what ADM equations look like for this collapse model, which is a 1D collapse, and then what numerical schemes are used for this for looking at this collapse scenario, and finally, you have the boundary conditions and the initial condition, and then what really happens when the code runs. That is what we're going to see. Okay. So So what you have is, so I will not be deriving the equation, but you can always look up these things. It's given at various places. So what you basically do is we start with the Einstein's equation. So you have so we work in the geometrized units where g equal to c equal to 1. Okay, there will be a lot of these things are something which you already done as part of the school, but this would be a good revision there. So you have this thing which you have the g Newton which is set to 1, c equal to 1. We usually decompose our space time. So decompose space time. This is the 3 plus 1. So then you have your slices given by t equal to constant surfaces. So that sort of gives you a foliation. Given a foliation, you generally have the 4 metric is therefore then given by minus alpha square plus beta I. Okay. The notation here is that ij's all go from 1 to 3, alpha, beta go from 0, 1, 2, 3. It's very different from what I usually follow, so it's difficult for me as well, but just for I usually flip the two. Okay, so so you have the metric, and the similarly you have the inverse of this, and the inverse is minus alpha 1 by alpha square, beta I by alpha square, and then you have beta j by alpha square, gamma ij minus beta I. So you just have these two. Okay. So here alpha is known as the lapse function. It simply shows that when you are advancing your time by t plus delta t, so you are going from 1 sigma to sigma t plus delta t, how does your time lapse happens? Okay, so that's the amount of time lapse that is given by alpha with every time step delta t. Beta I is basically your shift vector. It tells you that when you have taken a point P and gone from one surface to another, this point P will not go to the same point, but you have to shift it to come back to the same point. So if this is the xi equal to constant, so this would be your evolution in time. It will take you from P to P prime, but if you want to get back to this thing, so you have to shift your P accordingly. And it depends on your foliation. That is, when our space-time is defined, is foliated in this way, where gamma ij is telling you the metric on the 3 slice. The shift is telling you that how the foliation has happened so that this would be there. So in general, these two surfaces are different. Okay? It may happen that you can choose a gauge where beta is 0 for all t. Okay? Then you will not have any shift. It should be there. Okay, so that's one of the possibilities. So it's a gauge choice which is present to you. So therefore, the general line element which would be there is simply ds square is minus alpha square dt square plus gamma ij dxi plus this dxj plus beta j dt. Okay, which I can also combine dt terms together, so it can be written as minus alpha square plus uh, beta is basically just that beta I dt square plus 2 beta I dt dxi plus gamma ij dxi dxc. Okay. So with this coordinate setup, one can take this Einstein's equation and you can compute what they give. So with this coordinate choice, the Hamiltonian constraint turns out to be 3r plus k square minus kij minus 16 pi rho 0. Okay. So that is one Hamiltonian constraint in this form, where 3r is the Ricci scalar compatible with gamma ij, just the spatial metric, and kij is the extrinsic curvature, and k is just gamma ij kij, the trace of the extrinsic curvature. And then you have this rho. Rho is essentially gives it's n mu t mu nu. So you have the t mu nu over there. So this is the energy density. So where are you getting these n's from? N's are essentially the normal vectors which are unit normals to the time coordinate, which are basically doing the time evolution. So n mu is essentially is just time-like vector. So this is minus alpha 0. So tilde is just vector notation for this, and you can find n mu is alpha inverse minus alpha inverse beta I. Okay, so they obey the rule that ni n mu is minus 1, and also the fact that you can define what is called the projection operator. If you take any tensor, you use this projection operator, dot it with that tensor, that will give you that tensor on the surface. So this projection operator is simply P mu nu is delta mu nu plus n mu n nu. And then you can of course show that n mu p nu mu is 0. So if you take any tensor that you dot that tensor with the projection operator, it will project it onto sigma, the space-like surface which is there. So if I want to look at the what are the evolution equations in this case, oh, by the way, there is also the Hamiltonian constraint is there, then there is also the momentum constraint. So let me just write the momentum constraint over here. There are two constraints. Momentum of the diffeo, that is mi is dj kji Ti of k, and then you have just like you have the energy density over there, so you need to have some sort of a momentum current. So this is 8 pi Si equals 0. So this Si is, you take the original TAB, so you have the T mu nu, dot it with 1n, so n nu. So this will give you the flux of in the particular direction, the momentum thing, and then you project it. So P mu I. Okay. D is the Di is the covariant derivative that is compatible with gamma ij. So the three covariant derivative. So essentially di of gamma ij is equal to, that gives you what the connections are in terms of gamma ij. So you have these things. So together with the Hamiltonian constraint, the momentum constraint, the evolution equations for Kij are then given by del T of Kij equals beta L del L Kij plus Kij del J beta L Kjl del I beta L minus di dj of alpha plus alpha times 3r plus kij minus 2 kil klj, and then you also have the the matter configuration, which is plus 4 pi alpha gamma ij s minus rho minus 2 sij. It's quite complicated. This is what it is. So this tells you the evolution equation for the extrinsic curvature. Once you know the extrinsic curvature, and then you also need the evolution equation, the second one, which comes out is for gamma ij. See, you have the Einstein's equation here. That is what there is. So that is what gives you, one of it gives you the Hamiltonian constraint, then you have the momentum constraint, then you have this thing, and then you have the fourth one is here. So this thing is just minus 2 alpha Kij plus di beta j plus dj beta I. That's all. Okay. So these four equations are called the ADM equation. So equation 3, 4, this one. Pardon? Yes. The spatial. Yes, yes, yes. On the only on the surface. The yeah, projected. Yes. So these four equations are called the ADM equations. So they define the whole. I mean, essentially, what happens is you have the Einstein's equation in the covariant form. What I've done is you've taken this coordinate system, uh, and then split it into all these four different parts. So once you have that, these are just equations for the gravity part. Then you need equations for the matter part. That is, you need to couple it with matter. Okay. So when you, sorry, yes. Pardon? Second term, this one? of the third equation, this one, yes. Yes. Oh, yeah, 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 yeah. So it should be uh, KIL. Correct. You cannot have that. Correct. So you need the matter part. Let's bring that down. So for that, what is consider is the minimally coupled massless field. So this is also called the ADM plus Einstein-Klein-Gordon system. So you have the action given by d4x root minus g r plus 16 pi minus half g mu nu del mu phi del mu phi. That's what you have. So for getting, so we have the two evolution equation for the explicit curvature and the metric. You need the equation of motion for phi. So those equation of motion, one thing we need is the energy momentum tensor. So energy momentum tensor for phi t phi is simply minus 2 by root minus g uh, delta L phi by del g mu nu. So this is del mu phi del nu phi minus half g mu nu del alpha phi del alpha phi. Okay, that's simple. Uh, so you have the Lagrange density for the field which is specified for you. So now we'll select a gauge choice for our slicing sigma t, okay, or the metric in general. So we'll work with spherical symmetry. Okay. In this particular case, the line element is given by ds square is minus alpha square, just a function of t and r, dt square plus a square of t and r dr square plus r square d omega square. Okay. So this thing is also called, it's working in the polar slash radial gauge. Okay. So essentially what we have done is we have chosen gamma rr to be a square. Okay. Gamma rr is a square, and then this coordinate r is basically the radial coordinate. So 4 pi r square gives you the uh, area of the sphere of a constant r. Now once you have this thing, let me sort of get back to this. Yeah, just a sec. Yeah.
I have just one question regarding ADM equations.
Pardon?
Regarding ADM equations.
Yes.
Einstein's equations, there are a set of 10 PDEs.
Yes. 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 Yes.
But ADM equations, they are 15, right? Because we have.
So you have gamma ij, which is again So there is a constraint. There's a Hamiltonian constraint and a momentum constraint. So okay, so the constraints also will reduce the set of equations. The total set of equations will not be yeah, yeah, yeah. Okay. So that's what the gauge choice also we have done. So the now we have only two variables to look at, alpha and a, in the most spherically symmetric form of the metric. So it's the most general metric which is spherically symmetric. So in this system, the Einstein Klein-Gordon equation is essentially obtained by taking this action which we had. Have I removed the action? Yeah, it's over there. So you vary this action with respect to phi. Okay, and what you get is uh, del t a by alpha del t phi equals 1 by r square del r square alpha by a del r phi. So it's the Einstein Klein-Gordon equation which you get. It's basically just the Klein-Gordon equation written for this coordinate. That's all. Okay. There's nothing fancy about it. But these are, so it's a second order equation. So in order to evolve it, you can break it into two first order equations. So you define therefore two auxiliary fields phi and pi such that your capital phi is, it's also a function of t or t and r, is essentially this del t phi, del r phi. Okay, think of this as coming with a slant, otherwise it mixes stuff. And pi t comma r is this one, a by alpha del t phi. I mean, I'm doing the same thing which anyone would do for, suppose you had x double dot is equal to f. So you define x dot is equal to v, and then v dot would be equal to f. So it's the same thing. So you essentially have this, and then once you have this, your this equation which is there, it breaks into two first order equations. So one of them is sort of easy to see. It's just so you are basically looking at time derivatives of both. So the first one is del t of phi. So del t of phi is del t del r of phi, um, which is del r of del t phi, and del t phi is alpha by a pi. So this is del r of alpha by a pi. And you have del t of pi, which essentially comes from the fact that pi is this, del t of this is this, which is this. So it's 1 by r square del r square a by alpha by a del r phi. But then this alpha by a del r phi is already is del r is capital phi. So this is so the second order equation is sort of broken down into two first order equations, and rho, which was n mu n nu T mu nu energy density is simply given by um, T of phi is alpha square T T of phi. This is only the time component. So this is phi square plus pi square by 2a square. Okay. And in this coordinate system, therefore, if I were to write what is my Hamiltonian constraint, because we are now considering a particular choice of coordinate system, so the Hamiltonian constraint and both the momentum constraint, they will be, sorry, where is that? I can write what these are. So these are essentially, the first one is 3r minus 16 pi rho, because k is equal to krr. So this is what it gets reduced to. And 3r for this metric gamma ij, which we have considered, is just 4 by r a square del r a by a plus a square minus 1 by 2r. Okay. So therefore, you can just substitute, rho is just phi square plus pi square by 2a square, and PR is this, so it can be substituted for the Hamiltonian. It's just a simple thing. So since we know that H is equal to 0, analytically the Hamiltonian constraint must be satisfied. So it gives us the equation del R of A by A plus A square minus 1 by 2R equals 2 pi R phi square plus pi square. So already you see one of the equations which is there, it does not really have any time built in. Okay, so it's like your Poisson equation. It's an elliptic equation. It's not hyperbolic equation. So it's an elliptic equation, this one. And then you also have the so one can calculate what uh, k theta theta and k phi phi, they are 0 for the slicing which we took. So they lead to uh, the constraint equation. So del T of k theta theta for all times. Since that is there, it implies the relation that it leads to the equation del R alpha by alpha minus del R A by A minus A square minus 1 by R equal to 0. This is this. So these are two equations which come up. So now you have essentially, so you have one equation which is here. Um, Let me just write this thing here. So del R of alpha by A pi. So it's equation 1, 2, and then you have equation 3 and 4 which are over here. So these are the 4 equations one has to solve in order to get what how gravitational collapse happens. Given profile for the scalar field. So if you specify a particular profile of the scalar field, these equations will tell you how the evolution proceeds. So Now the question is, how do we solve these equations on a grid? The first thing to notice is that, again, as I said, these two equations are parabolic elliptic equations, whereas these two equations, they are coming from the wave equation. So these are hyperbolic equation. What it means to you is that if I give you a slice and I give you data on that slice, that is what is the configuration, I can evolve that data forward for the wave equation. That is, you give me some function at time t equal to 1, I can tell you what is the function at time t equal to 2. Okay, so they have a relation between them. But these two equations, in order to get, so you have four functions essentially. You have capital phi, you have capital pi, you have a and alpha. So all four functions need to be evolved simultaneously, and all of them are functions of, so they are functions of t and r. Since they have to be evolved on a, so it's being a function of r and t, they're basically functions defined on a spatial grid and moving further in, so they're defined on delta r, the spatial grid separated by delta r, and moving every time step delta t. Okay. So in order to do that, the equations need to be put into, they have to be discretized. So discretized both in time as well as in space. Okay. So in order to do that, let me use this part of the board. So you have every point t and r. So this is where you use what is called finite differencing. Okay. So given a function f at point t and r, which is essentially given by n delta t and some j delta r. So therefore every point is specified by n and j respectively. So once you have them, so these are the radial and the step sizes. You will just use this notation. The function f is f and t comma j delta r is just f n j. Okay. So the notation is this. Then the derivatives of f with respect to, so this, the with respect to r and with respect to t, they can be defined. And now there are different schemes which are available to do that. You could, so a simplest one is, I mean, these are like, you have a grid which is there and some function which is defined. You could use the function on the left side minus wherever you are, divide by the delta r or delta t. That would be your this derivative. The other, so this is using the nearest neighbor either on the left, or you could use the nearest neighbor on the right. The method which usually is used is called the central differencing, which basically uses both left and right to define the derivative at that point. Okay. So in this scheme, del r f at a point nj is essentially f n j plus 1 minus, not j, but j minus 1. Since they are twice away, so you have a 2 delta r. Okay. And this is valid in order delta r square. Similarly, is have delta t f and j is f n plus 1 minus n minus 1 2 delta t, valid for order delta t square. So everywhere you see a delta of something coming, so you have del t of phi. So this would be phi n plus 1 j minus phi n minus 1 j divided by 2 delta t, pi n plus 1 j minus pi n minus 1 j divided by 2 delta t. So you have n plus 1 and n, though both are given to you. Same thing would be done over here. You take the n plus 1, keep them on the right hand side, take all the n's on the other side, make the equations look something like ax is equal to bx. You have to, whatever is coming on this side here, it's simple, but sometimes you have a complicated mess which comes on here. So you'll have an equation on this form. You have to take the inverse. So this would be n plus 1, this would be n. You take the A inverse, that tells you how the n plus 1 quantity comes out. Okay, so you'll have it in the form of a vector which is given to you. And in order to compute the inverse, there are different numerical schemes which are available. LU decomposition, for example, is the fastest one. It works. Okay, so if the matrices are sparse and things like that, that is something which will work. So this is what these things are. However, so this will work for this case, which is fine. But then there are these two equations which I told you there is no time thing there. Okay, so I mean you do not have a time derivative of a or alpha there. But these things are evolving in time. So how do you compute them? Of course, these things require you to give you what are phi and pi. So if you know phi and pi, then you can get what a and alpha are for every time step. Okay. So they are constraint equation which need to be solved. So for this, there is an additional derivative which is sort of scheme which is introduced. Rather than writing that delta r del r a as by using the central scheme, you could write it in a different way, which is let me actually do it here only. So we know the approximations. So what you introduce are called cell-centered derivatives, meaning you define points which are n plus and minus half, j plus and minus half. That is, you are advancing, let us say, half step forward. Okay. So this thing is, again, I'll tell you where this is something which is useful. Suppose you are solving a diffusion equation. Okay, and a diffusion equation is a 2D diffusion equation, x and y. So there is a derivative of time on the other side, and there's a Laplacian xy on this side. So you have del square by del x square plus del by del y square. So in order to do that, again, you have this function u of x comma y comma t, which you have to define on a grid, a 2D grid, and time-like temporal thing which you have to do. So of course, since you have a Laplacian, you have a derivative with respect to x, with respect to y. Fine. How do you evolve it forward? The system has to be solved. How the derivatives have to be solved on the grid. So derivatives are always there on the same time slice at the same time. Okay. So to achieve how the changes happen to the derivative to the function, let us say u x comma y at the next time step, rather than going from t to t plus delta t straightforward, you do what is called half time step. That is, you evolve it to delta t by 2. In the first time step, you keep y fixed. Don't change it, do anything to y. You find how it happens when you change x's. And in the next time, so you are doing the same thing, delta t, but in two ways, in two steps. So delta t by 2 plus delta t by 2. In the first one, you keep y fixed, change your x's. Then you keep your x fixed and change your y. So there's something called alternate direction implicit scheme, ADI scheme, which is what is used rather than doing both things together at the same time in one time step. It's something not possible. So you define these n plus half and j plus half, and these are essentially delta r f n plus half f n plus half minus f. So the n plus half remains the same. This is only changing r. So therefore this is this j plus 1 minus j by delta r. Again, valid only till delta r square. So that you have to keep small in order to have a proper derivative. So the grid size should be as small as possible. Of course, it depends on the memory of your system. If you make it too small, your memory allocation will be a problem. So you need to take that into account. So, and then you have del r f n minus half j minus half is f j n minus half. So this is j plus 1 j, and now you're doing j and j minus 1. Again, we used central differencing, that is at any point I and j, n and j, you use the left value and the right value, j plus 1 j, get this thing down. The half is using j plus 1 and j, the half so half step in the radial direction, the derivative is j plus 1 by j, backward will take the backward value. And then once you have these two, in order to get your usual ones, you take an average of both. So Fn j plus minus half is half Fn j plus minus 1 plus Fn j r square. So this is for this thing. You can also do the same thing for the time step, and for the time step, just a second. This question, yeah.
What do you do at the boundaries?
Yes, yeah. So boundaries will see what will happen. Essentially, what will happen is this delta r of any function would be set equal to 0. Okay, so that will come. So just like I have defined delta r's, the derivative with respect to r, I have a derivative with respect to time f. This thing is n plus half j plus half, and similarly f n plus half j plus half, j minus half. So these are, so this is changing time. So this is plus half, so n plus 1 minus n. I'm just going to write that straight away. So this goes for a ride, and you have delta t, and of course valid till order delta t square. And then you have this one, which is n minus half. So you automatically know it is going to be n minus 1. So this is n minus n minus 1, j minus half delta t. Okay. Of course, both of them valid order delta t square. So we'll be stopping soon. Okay. So with this, With these definitions, all you need to do is you need to discretize all these four equations. So you have 1, 2, 3, and 4. So let us see what they become. So this one is just again derivative with respect to time. So this is just phi n plus 1 j minus phi n minus 1 by 2 delta t. This n plus half and all we will use for the elliptic equations. So these will just be the usual ones, which are equal to 1 by 2 delta r, this one. Alpha by this thing is just alpha n. So derivative with respect to r, so this would be j plus 1 minus j. So j plus 1 pi j plus 1 n by a n j plus 1 minus alpha n j minus 1 pi n j minus 1 by a. That's it. So that's your first equation. Gone. For the second one, this is 1 by r square del by del r, which is essentially, so you multiply by 3, divide by 3. So this is 3 del by del r cube. So therefore you have, this one is the same thing here, pi n plus 1 minus pi n minus 1 j. This divided by equal to 3 divided by r cube. So this is r cube j plus 1 minus r cube j minus 1. So 3 in this case is an exponent, not the n which is was there. So it's r cube, r square j plus 1 alpha n j plus 1 by a n j plus 1 minus r square j minus 1 alpha n j minus 1 . That's it. So these two equations are just these. They are discretized in the following way. Now we need to take care of these elliptic equations. So for the elliptic equations, the discretization is, so you have, so if you first look at the polar slicing condition, that is the derivative of t being equal to 0, this one is essentially, consider del r a by alpha minus del r a by a So since we know that this is true for all times, so therefore it is true for n plus 1 j plus half equal to 0. Okay. So since we know what is our j plus half given an n plus 1, using this one, the the averaging which we did over here. So using both the average as well as the half values, this essentially gives us, so this one gives alpha n plus 1 j plus 1 minus alpha n plus 1 j by delta r plus half alpha n plus 1 j plus 1 this aj n plus 1 plus a n plus 1 j plus 1 square r j plus half minus 2 by delta r a j plus 1 minus aj equal to 0. So it's a lot of work, but once in your lifetime you should work it out. After that you have written a code, then you don't need to. So so this is the third equation, and then there is the fourth equation. But for the fourth equation, you see there is del r a by a, which is being computed. It is only a function of a coming from phi and pi. So we define uh, a capital A j I as log of a j I. That makes things easy. So you therefore you will have an equation in terms of capital A. So essentially it is again it's a bit complicated to write, but okay, still let me just write it down. So this one is the fourth equation is capital A n plus 1 j plus 1 minus a n plus 1 j by delta r plus exponential, because there's that term, extra term which is over there. The first term is simple, that is just del r by del r, that is the log of a, using that is just a. This one is a j plus 1 n plus 1 minus a n plus 1 j minus 1 by 2r j plus half then you just have the phi and pi. So those are just phi square plus pi square. So there's nothing fancy about it. So but bring it to this side is just minus 2 pi r j plus half phi n plus 1 j plus 1 plus phi n plus 1 j square plus half pi n plus 1 j plus 1 square equal to 0. So what does it tell you? It tells you that we had 4 equations. 2 of those were first order equations. They were first order in phi and pi, capital Phi and capital Pi, which we got as auxiliary variables because we had to convert the second order equation, the Klein-Gordon equation, into 2 first order equations. That was cool enough, nothing fancy about it. Those were hyperbolic equations. So therefore, they were fairly easy in the sense that you give me n plus 1, the n minus 1 is here. So I just take this n minus 1 to this side. Okay. So n minus 1, all these n minus 1 are taken there. So you just need n and n minus 1, both are present to you. So this just becomes a matrix equation. After all, this would be a diagonal equation. I mean, on this side, the matrix, remember I wrote ax n plus 1 is equal to bxn. So on this side you will have this 1 by delta t diagonal matrix with all the values, this thing, and the other side you have this. You just have to, in order to get what is happening at the next time step, you just need to take the inverse for both of them. Now alpha and a, on the other hand, were given by the constraint equations, which are to be satisfied at a given time slice for all times. They do not have time, for there is no time derivative of a, there is no time derivative of alpha. So therefore, but there is phi and pi. So what happens is, you give me a field configuration. The field configuration evolves given the background A, but then you also have to involve the background, because this all has to be self-gravitating or self-consistent. So in order for that to happen, the phi and pi will feed into the constraint equation, which are valid for all times. Since you know that they are valid for all times, I need, at every time I need phi n plus 1 and pi n plus 1 to be fed in, and what change has happened to them, that will tell me what change will A will have. So that is why you considered these two equations at n plus 1 and j plus half, then is a half time step, in which you are considering the n plus 1 and n minus 1 together, but in half time steps. So both we defined the half and the, where did it go? Disappeared. So we defined those, and they basically took care of the left and the right in half time steps each. So when that is done, this is defined in, and the total is basically given by the average of the both. So once that is there, you then have alpha n plus 1. The next time step, alpha, is given in terms of, where is that? So here there is no pi happening, this is just an algebraic equation. So there is no pi here or anything like that. But in this one, you see that capital A is given by phi n plus 1 at that time step. So once we have solved we have gotten this thing, we take this, put them here, and get the updated value of capital A. Capital A is just log of small a, so that gives us small a. You take this small a, substitute it here, and get alpha. So the number of differential equations we are basically solving are 2 here. Then this is the second one. This is also a differential equation. This is an algebraic equation. Okay. There is a complexity which is involved, in the sense, as I said, because you have two elliptic equations and two hyperbolic equations, the one hyperbolic equation into two parts. This thing is easy, but the elliptic equation requires certain thing. That is, because you want, I mean, this one is fairly simple. This is just algebraic equation, nothing fancy. But this one makes computing expensive. Why? Because alpha, the next alpha, is to be computed all across the spatial grid. And how does it change from one to the next grid depends on how phi and pi have changed and the derivative of A. So it has to update, given what you know the value of capital A at one point j, it has to update everywhere. So the method which is used here is something called the Newton-Raphson solver method, or the shooting method. So that is something which is used here. So this is basically how discretization proceeds. Tomorrow we'll take a look at how to, of course we have the grid here, but we use what is called uniform grid. But when you are taking a look at a black hole collapse, for instance, or a gravitational collapse, whether or not it will form a black hole or not, you know that for certain values event horizon will form. Since your event horizon will form, you do not want to sample your spatial grid uniformly, but rather need to have a resolution such that wherever things are changing a lot, you need a higher resolution compared to where things are not changing by much. So there is a way to do it, which is by using non-uniform sampling. So that is something which I mentioned tomorrow. There is another way which is called adaptive mesh refinement. That, so in the uniform sampling, the non-uniform sampling, you have used a non-linear function to make your grid non-linear at one point. and it stays like that forever. Okay, but there is a technique called AMR where you can actually adaptively change your grid, but we'll not consider that. That's also something which is being used, but we'll take care of the non-uniform sampling tomorrow. Okay, and see what happens there. Okay, I'll stop here.